Alright guys, welcome to the UNSW MathSoc workshop for the Math 1131 and 1141 course. Today we're going through our second topic in this course, which is calculus. So the first hour of this workshop will involve going through the first 5 topics of calculus, which are listed here. Alright, so to start, we're starting off with the topic sets, inequalities, and functions. So this is quite a straightforward topic and doesn't really get tested in your actual exams. So we're just going to go through some questions. So question 1, part A, prove that fx is equal to 1 plus x squared is positive for all real numbers x. So part A is quite straightforward. We can just do it by completing the square. So as you can see, that's what they've done here. So because x is a real number, x plus half, which is also a real number squared, is obviously positive, plus 3/4, which is also positive, and then the answer will be greater than 0. Now moving on to part B, by considering cases or otherwise, prove that this expression here is always positive as well. So to do this question, they already gave us a hint that we should be considering the cases. So the first conceptual realization you need to make in order to do this question is to realize that it's a geometric sequence. So when we're dealing with geometric sequence, recall that we have different formulas for different cases depending on the magnitude of our ratio x. So here I've listed when the magnitude of x is equal to 1, then we can just do this by simple calculation. F1 is equal to 5, which is greater than 0. And then f minus 1, which is equal to 1, is also greater than 0. And then the second case we have here is when the magnitude of our x is smaller than 1. So recall we just apply the formula a of 1 minus r, where a is our first term, which is 1, and then r, which is our ratio, is x. So because we've been given that the magnitude of x is smaller than 1, as you can see, our denominator here must be greater than 0, and so is our numerator. And so we say fx when the magnitude of x is smaller than 1 is also greater than 0. Now lastly, we have the magnitude of x being greater than 1. So we use this particular formula over here. And then here the case is slightly more complicated, so we need to break it down into 2 further subcases, if you like. So firstly, we have when x is positive, then as you can see, the denominator and the numerator will both be positive because recall the magnitude of x is greater than 1. And then secondly, when x is negative, the denominator and the numerator will now be negative because we have odd power here. So this x to the 5 and the x minus 1 will be less than 0. And so we know when we have the first case here, then positive divided by positive will end up with a positive number. So that's greater than 0. And then next, we have negative divided by negative. So again, we end up with a positive answer. So part C asks us to generalize the above results. So here I've written that the generalized result is 1 plus x squared and plus all the way to x to the power of n. And then the argument for part C is basically the same as what we've done in part B. So we're considering the 3 cases using the fact that what we're dealing with is a geometric sequence. Although the only thing you need to consider is what assumptions are we making here. So if you think about it, if instead of x to the power of 5, we have x to the power of 4 or x to the power of 6. So when we have even powers, then this wouldn't hold true, because when we have x is negative, then we end up with a positive numerator but a negative denominator. So that breaks our case of if x is greater than 0. So the condition that must be satisfied here is that our n must be odd. So that's a very important condition that's not stated in the question, but you need to consider when you're doing it, when you're generalizing the result you got from part A and B. All right, moving on to our second topic, we have limits. So a reminder that these workshops that Math Society is hosting, the purpose of these workshops is mainly to go through some exam style questions that help you prepare for your exams. We do occasionally have bits of theory that we cover to help you with these questions, but this is not a comprehensive guide in terms of the theory. So we only have little bits. So that's something you might want to keep in mind. All right, so the first definition we have to help you remember what the epsilon m definition of a limit at infinity is. So it says here, suppose that L is a real number and f is a real valued function defined on some interval b to infinity. We say that the limit of fx as x approaches infinity is equal to L if for every positive real number epsilon, there is a real number m such that if x is greater than m, then the absolute value of fx minus L will always be smaller than epsilon. So this is a definition that might be a bit harder to understand just by looking at the words. So if you're a visual learner, you can have a look at the diagram over here. So essentially what this definition is saying is that if this particular limit exists, then there exists a real value m such that for all x greater than m, so for all values of x on the right hand side of our m, then our function fx will always be contained within these two boundaries. And so these two boundaries are defined by L plus epsilon and L minus epsilon. So that's exactly what we have here on the left hand side. The absolute value of fx minus L simply refers to the distance between L and our function fx. All right, then let's go through an example question. So this question is straight from a MATH1131 exam. So the question says, use the epsilon m definition of the limit to prove that the limit of this particular expression over here as x approaches infinity is equal to 2. So now let's go through the solution. So here, because our expression here approaches 2, we know that our L is equal to 2, which is exactly what's being stated. So let L be equal to 2. Then if x minus L, substituting in what's being given in the question, you get this. And then what they've done here in the second step is that they've taken out the ex on cosh x. So they're left with this expression inside the absolute values. And then recall that the definition of cosh x is half of e to the power of x plus e to the power of minus x. And so what we have here, 2 cosh x over x to the power, or e to the power of x, will simply be equal to this. So if there's a bracket, then we end up with 1 plus e to the power of minus 2x. All right, then the 1's cancel out, and then we're left with this expression over here. Now, because we know that cos x is always greater than or equal to 1, so our fx minus L, which is our expression here, will always be smaller than or equal to e to the power of negative x. So what we can do with this result is to say that, remember, throughout when we're doing this question, we have to constantly come back to this epsilon m definition or limit at infinity. So that's exactly what we've done here. So because we know that fx minus L will always be smaller than or equal to e to the power of negative x, and we know that in order for this limit to exist, then this must be smaller than epsilon. And so we can say that for this to be true, then e to the power of negative x must be smaller than epsilon. And this will only be true if this expression holds true. So you can get this just by doing some simple algebra. So you move the negative x down. So now what we've established here is that if our m is equal to the log of epsilon to the power of -1, then we've successfully shown that for all x greater than m, so this value here, then there exists an epsilon greater than 0 such that this value is smaller than epsilon, which is our definition of limits at infinity. So essentially, by doing all these calculations, what we're really trying to do is to find a relationship between our m and the epsilon, which is exactly what we got here. All right, now moving on to our question 3, which is from a MATH1131 exam in 2011. So the question says, evaluate the limit of this. All right, so this is a bit simpler than our question above. But before we can do this question, the first thing we need to do is to rationalize the denominator. The reason why we have to do that is because without rationalizing, as I've done here, you actually end up with an indeterminate form. So a 0 divided by 0. And that's not a nice thing to work with. So instead of doing what we usually do with limits straight away, we have to first rationalize the denominator. So we do that by timesing both the numerator and the denominator by the conjugate of our denominator. So the conjugate would just be x plus x squared minus 6x minus 4. So that's exactly what we've done here. And then because we can simplify the denominator, we end up with x squared minus 6x minus 4. And then that simplifies further to 6x plus 4. Now that we have a nice and rationalized fraction, we can then do what we usually do with limits. So we divide by the highest power of x in the denominator to obtain this particular value over here. Sorry, this expression over here. So as you can see, as our x approaches infinity, all of these terms will become 0. So what we end up with is 1 plus root 1 all over 6. So that gives us 1 on 3, a third, which is our final answer for this question. I guess the only thing you might want to be aware of is that if you divide everything by x, when that goes into your square root, that becomes x squared. So that's just something to be careful of. Now moving on to our next topic, we have properties of continuous functions. So one of the most important theorems covered in this particular topic is the intermediate value theorem. So basically the intermediate value theorem states that suppose that f is continuous on the closed interval AB, then if z lies between fa and fb, then there is at least one real number c in this particular interval such that fc is equal to z. So basically what this particular theorem is talking about is that if you have a value z that lies between our fa and fb, then this particular function, our fx, will have to go past z at least one point. So as you can see, in this particular example here, our fx has passed through z 3 points, so c1, c2, and c3. So remember, we're only looking at the interval AB here. So our FA is, if you like, a boundary point of fx, and our FB is also the other boundary point. So that's our intermediate value theorem. Now, to practice the application of this theorem, we can look at an example question. So the question says, consider this particular function over here for all real x. Now, part A, use the intermediate value theorem to prove that f has at least one positive real root. So remember, when we're talking about a root of this function, or a zero of this function, we're talking about when fx is equal to 0. All right, so before we can apply our intermediate value theorem, let's first consider the conditions that we need to satisfy before we can do that. So if we go back to the theorem, it says here that f has to be continuous on the interval we're dealing with. But that's not really an issue because we know this is just a simple polynomial and it's obviously going to be real for all real x. So here, that's the first thing we've stated. We've said that f is continuous on the closed interval 0, 2. So that's to tell the marker that you've satisfied the condition that to apply the intermediate value theorem. All right, so this particular interval that they've picked over here, so 0, 2, is entirely arbitrary. So you see later that why they've picked this particular interval. So the next step for applying the intermediate value theorem is to calculate the values of our endpoints, so our boundary at the boundary. So here we've calculated f0 to be -5, which is smaller than 0, and then f2, on the other hand, is greater than 0. So as you can see here, that one of our endpoint is smaller than 0, and one of our endpoint is greater than 0. So when you're picking your interval, as long as they yield in a negative number and a positive number, it doesn't really matter what you pick to be your interval. All right, so the conclusion of our part A is that by the intermediate value theorem, because our endpoint is above and below the x-axis respectively, then f has at least one positive real root in the interval 0, 2. So in other words, it's saying that between this, within this interval 0, 2, f passes through the x-axis at least once. Now part B is closely related to part A. It says here, by considering f dash, so the derivative function of our fx, or otherwise, show that f has only one real root. All right, so because they've suggested us to consider f dash, that's exactly what we're doing here. So since f dash x is equal to 3x squared plus root 3, so that's just some simple differentiation. This whole expression here will always be greater than 0 because, as you can see, we have a square, which is always positive, plus a positive constant. So we always end up with a positive gradient function. Because our f dash x is always greater than 0, we say that the function will be increasing. So the gradient is always positive. And hence, f has at least one real positive. Hence, f has exactly one real positive root. So because it's increasing, it doesn't have turning points like we do with this example here. And so we know our fx can only pass through a certain point once throughout this interval AB. So even if our question doesn't ask you to consider f dash, so even if you're not provided with this particular hint, you should be able to link this question. So you should be able to link a question asking about the number of roots of the function f to the derivative of the function. Because remember, if our function is decreasing or increasing within this particular interval, then we know for sure that it only passes through each point once. So it's only going to have one real positive root. The reason why they also said positive here is simply because they had the interval 0, 2. So we know that our root has to lie between these two particular points. But that's not asking the question. So it's not necessary to include a positive. Although if it is, then you have to be extra careful when you're choosing your interval in part A. Right, moving on to our next topic, which is differentiable functions. Now we go straight to a practice question, which asks us to consider this particular piecewise function here. And then part A, given that the limit of x times a to the power of negative x as x approaches infinity is equal to 0, evaluate the limit here. So because we've been given a particular condition in this question, so when we're trying to evaluate the limit, what we should be trying to do is to write this in the form of this. In other words, to write this such that we can apply our condition somewhere in our solution. So if we look at our solution, that's exactly what's being done here. So this is what we started with. And then basically we multiplied both the numerator and the denominator by a h. So we end up with this expression here. So you probably noticed that this expression, e to the power of negative x, which is exactly what we've been given in the question. So using some basic operations with limits, we know we can break it into two distinct limits. So this is what we're trying to apply our condition into. Now, if we want to apply our condition, which involves x times a to the power of negative x, the assumption we're making here is letting x to be 1 on h squared. And so because the limit we're dealing with is when h approaches 0, and we know in this particular substitution, as h approaches 0, our x here will approach infinity. So we can rewrite this expression as this, which is exactly identical to the condition we've been given. And so we know from our question that this is equal to 0. And then over here, our limit of h as h approaches 0 is obviously going to be 0 as well. And so our final answer will simply be 0. Moving on to part B, we have, using the definition of a derivative, determine whether f is differentiable at x is equal to 0. So this is a very typical question where they ask you to determine the differentiability of a function at a particular point. So what we do with this kind of question is to take it into two steps. So the first thing we need to prove in order to prove the differentiability of a function is to prove that it's continuous at this point. And then the second thing we do is to prove that it's smooth at that point. So smooth is, I guess, another word for saying that it's differentiable. So it doesn't have any sharp turns or anything like that. So firstly, to prove continuity, recall that in order for us to prove that a piecewise function is continuous at its boundary, what we simply do is to take the limit of the function as our x approaches 0 from both the right-hand side and the left-hand side. So as you can see, that's exactly what we've done here. So as x approaches 0 on the positive side, on the right-hand side, our function approaches 0. And then as our x approaches 0 on the left-hand side, our function approaches 0 also. And then because at x is equal to 0, our fx is also 0, we know that fx is continuous at x is equal to 0. Now moving on to our second part of proving differentiability of a function, we're going to be using the definition of a derivative. So recall that's what we've been asked to do in the question. So using the definition of a derivative. So the definition of a derivative is when the limit of this particular expression, fx plus h minus fx over h as h approaches 0, if that particular limit exists, then we know our function is differentiable at x is equal to 0. So because we're dealing with this particular point, we just have to substitute 0 into our x. And then our fh is simply e to the negative 1 on h squared as given in the question. So we just substitute h for x. And then our f0, which was given in the question again, is just 0. And then you might realize that this expression here is exactly what we worked with in part A. So we know this to be 0. So now you should be able to say how part A and part B of one question is usually very closely related. So you should always be looking at the result from part A to see if you can use it somewhere in part B. So because this particular limit exists, which is equal to 0 from part A, we know that fx is indeed differentiable at x is equal to 0. Right, moving on. And just to answer a question in the chat, yes, these slides will be available. And then the recording of this session will also be available on YouTube. All right, okay, moving on to question 6. Consider this another piecewise function over here. So again, remember in differentiable functions, they always like to ask you about piecewise functions because really it is when you're dealing with piecewise functions that you really need to consider whether at this boundary point your function is differentiable or not. So part A explains why f is differentiable everywhere and hence determine f-x, so the derivative function. So again, we are trying to determine the differentiability of our function. So what we can do, as what we've done in our previous question, question 5, we first need to prove that it's continuous at this particular point, which is our boundary point, and that it's smooth at that point as well. So firstly, because our question is asking why f is differentiable everywhere, that's a bit different to our previous question where we only asked whether f is differentiable at one particular point, which is x is equal to 0. So one extra step we need to add into this question is to say that away from 0, f is differentiable. The reason why is because we're very familiar with our functions y is equal to x cubed and y is equal to x squared, and we know for sure that these functions are differentiable everywhere on the domain. So the only thing we really need to worry about is the behavior of our fx at the boundary, which is x is equal to 0. So what we've done here is that the limit of our function fx as x approaches 0 on the right hand side and 0 on the left hand side. So the behavior of x is identical. So both of these limits are equal to 0. And so we say that f is continuous at x is equal to 0. So that's our condition 1 done. Now moving on to the second part of our proof, we have to say that it's smooth. So what we've done here is that the derivatives of the two constituent functions are equal at x is equal to 0. So the derivative of our first function, x cubed, will simply be 3x squared. So when x is equal to 0, then we know that's going to be 0. Similarly, we have 2x here as our derivative. And then again, when x is equal to 0, our derivative will also be equal to 0. So that's what we mean when we say the derivatives of these two constituent functions are equal at the boundary, which is x is equal to 0. And note that this is a different way of proving why a function is smooth than what we did in our previous question, which was using the fundamental definition of derivative. Now this is a lot easier than the more rigorous definition that we went through before. But because in our previous question we're being asked specifically to apply that formal definition, so we have to do that. And then here it's not a requirement, so that's why we can just simply use the derivatives of both our constituent functions to calculate, to conclude that our function is in fact smooth. And so by the split function theorem, f is differentiable at x is equal to 0 and hence everywhere as required in our question. Now the second half of our part A is to determine the function f dash x. So that's basically what we've done here. So we know that the derivative of x cubed is just 3x squared, and then the derivative of x squared is just 2x. So putting that in, combining it into f dash x, that's what we end up with. So that's pretty straightforward. Now moving on to part B, we have explained why the function g defined by gx is equal to f dash x is continuous at x is equal to 0. So here again, we're dealing with a question that asks us to prove that something is continuous. So what we do is to look at the behavior of our function f dash x as x approaches 0 on the left hand side and the right hand side. So that's very similar to what we did previously. And then because these two limits are equal, we know f dash is continuous at x is equal to 0. Finally, we have part C, which asks us to use the definition of the derivative to determine whether g is differentiable at x is equal to 0. So again, this is probably getting a bit repetitive, but yes, we are again trying to determine the differentiability of our function. But because we've already evaluated or decided in part B that our function f dash x is in fact continuous at this point, then we can skip the continuity part and go straight to the smoothness by applying our definition of our definition of a derivative. So recall this is our definition, which we did in question 5 as well. Now the only difference between what we're doing here and what we did in question 5 is that we have to look at this particular limit when h is approaching 0 from the left-hand side and the right-hand side separately, because we'll be dealing with two different functions. So remember, on the left-hand side, so on the left-hand side of L0, we'll be dealing with the function 3x squared, and then on the right-hand side, we'll be dealing with the function 2x. Now that's very different to our question 5, where on the right-hand side and the left-hand side, we'll be dealing with e to the power of negative 1 on x squared. So in this particular scenario, as you can see, we don't have to consider the behavior of this limit from two different directions. So that's what we've done here. So this is on the left-hand side, we use the function 3x squared, which we substitute h to be 3h squared. And then on the right-hand side, we're dealing with the function 2x, so we substitute h into that to be 2h. Now, as you can see, as our h approaches 0, our first limit becomes 0. Although for our second limit, as h approaches 0, because these two h cancel out, we end up with a 2. So as you can see, the behavior of a derivative function as h approaches both sides of 0 are not identical. And so we say that f dash is not differentiable at x is equal to 0 because this limit, which is our definition of a derivative, does not exist at x is equal to 0. Right, now to look at the last topic before we go on a small break in between this workshop. Our last topic is the main value theorem. So recall that the main value, that if is continuous on the interval AB and differentiable on the open interval AB, then there exists at least one real number C in this interval such that this particular expression holds true. So again, this is something that can be a bit harder to understand just by looking at the text. But in case you forgot what the main value theorem states, we can have a look at the diagram over here. So essentially, the left-hand side of our expression over here, fb minus fa, all over b minus a, is simply referring to the gradient of this line. So this line is basically a line connecting our endpoints a and b. So rise over run, so our rise will be fb minus fa, as we have here, over run, which is our b minus a. So this is simply the gradient of our line AB. Is equal to f dash c. So our f dash c is simply equal to the gradient of our tangent to fx at this point c. So what main value theorem basically states is that there exists at least one point c where the gradient of the tangent at c is equal to the gradient of this line AB. So now it might be a bit easier to understand. So left-hand side is the gradient of AB, and then right-hand side is the gradient of the tangent here. Right, now to look at, go through a question. Question 7 is from a 1141 exam again. So the question says, assume that differentiable function f on R is such that f dash x is smaller than or equal to 1 for all real x. Given that f2 is equal to 2, show that fx is greater than or equal to x for all x that's smaller, or equal to 2. So here you can see that the question already established that our function f is differentiable. So remember, a differentiable function has to be continuous as well. So that satisfies our condition for applying the mean value theorem. The hardest part about our question 7 is to recognize the fact that it involves the application of the mean value theorem, because as you can see, it's not stated anywhere in the question. But that just comes with experience, and as you can see, the condition we've been provided within this question is also a hint for us to apply the mean value theorem, because we know this particular function satisfies the conditions imposed by our theorem. So because we are putting these two together and we're telling you that we need to apply the mean value theorem in this particular question, we can substitute all our values straight into our equation here. So if 2 minus fx over 2 minus x is equal to f dash c for some real c. So the interval that we picked here is x to 2. The reason why is because we are given in the question that x has to be smaller than or equal to 2. And so the interval we have here will just be x to 2. So fb minus fa, f2 minus fx, and then b minus a, so 2 minus x. So we know by the mean value theorem that there exists at least one real number c such that this expression holds true. Now, we've been given the question that f2 is equal to 2, so we can simply just substitute that into our equation, f2 is equal to 2. And then, because we know our f dash x is more than or equal to 1 for all real x, so we can replace our f dash c with more than or equal to 1. Rearrange the function, we end up with exactly what we need. Right, so that's pretty straightforward as well. So as you can see, the hardest part about this question is to identify the fact that you do need to apply the mean value theorem, but the calculation itself isn't really difficult. Okay, another theorem that we covered in the topic mean value theorem is L'Hopital's rule. So L'Hopital's rule basically states that suppose that f and g, sorry, just to answer a question from the chat, can you take the closed interval from a to x? In this particular case, you can't, because it says that x has to be smaller than or equal to 2. So if you write instead x 2 to x, where our 2 is our a, then it doesn't work because we know x is more than 2. So 2 has to be on the right hand side of our interval. Okay? Now moving on, so L'Hopital's rule suppose that f and g are both differentiable functions and a is the real number. Suppose also that either of these two conditions, so condition 1, condition 2, so either one of these two conditions hold true. And our second condition is that this particular limit has to exist. Then we can say that the limit of f(x) on gx as x approaches a is equal to the limit of f dash x on g dash x as x approaches a. So as you can see, for L'Hopital's rule, in order for you to apply this particular theorem, you have to satisfy both of these two conditions, so condition 1 and condition 2. And then in condition 1, you also have to, if you like, sub-conditions. So either one of these two must be true in order for this particular theorem to be applicable to your question. So the practice question we're going to do is, let f be a continuous function on R. So this is how we define gx, and then our f will just be a continuous function on R. Use L'Hopital's rule to show that if dash 0 exists, so that's the condition we've been given. So by looking at that, you should immediately relate this particular condition that we've been given in the question to the two conditions that must be satisfied for L'Hopital's rule. But we'll be able to see that how that comes into play later on. All right, so use this particular condition to prove that this limit of gx as x approaches 0 is equal to f dash 0 on 2. So as you can see, the limit of gx, so the limit of this expression over here as x approaches 0 is quite difficult to evaluate on its own. So what we can do is to apply L'Hopital's theorem. Before we do that, we have to see if both of our conditions have been satisfied. So we start with condition 1. So as x approaches a, in this case we have a is equal to 0, as you can see. So basically as x approaches 0, then both fx and gx either approaches 0 as well, or they approach infinity. So that's exactly what we've done in the first step here. So if we call the numerator ax and we call the denominator bx, we're basically saying that lim x approaches 0 of ax is equal to this. And then same thing, we have bx here. So as you can probably see already, so as our x approaches 0, both of our functions ax and bx approaches 0. So that satisfies our condition 1. Right, so just to go through how we got that, so if x approaches 0, this would be 0, and then this would be 0 as well. So from 0 to 0, our integral here will be 0. So 0 minus 0, we have 0. And then this is a bit more obvious. So we have 0 squared, which is 0. So because we now have condition 1 satisfied, then we can look at condition 2. Okay, so condition 2 is for this limit to exist. But the special thing about this particular question is that you can't actually come to conclusion right now whether our limit, this limit here, exists or not. But then you see later on why we can conclude that condition 2 has also been satisfied in this particular question as well. So here we're just applying L'Hopital's theorem, or L'Hopital's rule, by taking the derivative of both our ax and our bx. So if we apply the derivative to both of our functions, then we end up with, as you can see by the fundamental theorem of calculus, we end up with fx minus, because our f0 is just a constant, so this minus f0, so we get rid of the x. And then for the denominator, for the bx, we just end up with 2x. But then this is also hard to evaluate as well. So what we actually need to do is to reapply L'Hopital's theorem. But I guess before we can do that, we have to check again whether our conditions, in particular our first condition, is satisfied. So to check that, we have to say that the limit of as x approaches 0 of fx minus f0, which we can see to be if 0 minus f0 is just 0. And then for our denominator, you can see as x approaches 0, it's quite obviously going to be approaching 0 as well. And so again, our condition 1 has been satisfied, so we can reapply L'Hopital's theorem right here so that we end up with this particular expression over here. So as you can see, we're taking the derivative of the top, so it becomes f dash x, minus, we can just get rid of the constant, and then on the denominator, we just end up with a constant 2. And so as x approaches 0, we know this is what we end up with. Now remember, we've been given in the question that f dash 0 exists. So we know this entire thing, this entire expression here will exist as well. Now let's really think about how our condition 2 comes into play. So maybe you have realized already, because we've proved that this exists, then we know this limit exists. And then if that exists, then our previous limit will exist as well. So that's how we can say that for each of the 2 scenarios where we applied L'Hopital's theorem, we're dealing with a function where our second condition is satisfied as well. And so we can successfully prove that our gx will be equal to f dash 0 on 2, as required in the question. Right, so that brings us to the end of the first half of our calculus workshop. So we're gonna take a short break before we go on to the next 5 topic, which will be done by a different presenter.
Hello? Hello, can you guys hear me? Can anyone say in chat whether... Yep, okay, that's good. Alright, so I'll be your presenter for the second half. And we will be going through 5 topics, which are inverse functions, curve sketching, integration, logs and exponentials, and also hyperbolics. So the first topic we're going to go through is inverse functions. And in the test, there will usually be, for inverse functions, there'll be one main thing they test you on, which is the inverse function theorem. But there's also some other things that they'll test you on, which I will go through maybe 1 or 2 examples in the next few slides. So the first 2 theorems you have to know is the relationship between inverse functions and one-to-oneness. So suppose that f is a one-to-one function, then the inverse of f will be a unique function, f inverse, where the range of f inverse is a domain of f. So this is a useful theorem for when you want to prove whether something has an inverse function or not. Because if you can prove that the original function is one-to-one, then you're able to prove that the inverse function does exist. And the second theorem, which is the inverse function theorem, says that suppose that I is an open interval where f ranges from, where the domain of f is the interval I, and it goes towards the real valued, the real values, and it's differentiable, and f dash is not 0, then for all the values of x in this interval I, we have these properties, and also the biggest thing is that the g dash of x is equals to 1 over f dash gx, which is basically the core of the inverse function theorem. In this formula, g is the inverse function and f is the original function. This is the most basic form of this formula, but on the next slide I'll show you the alternative form of this formula that I prefer, which makes everything simple in my opinion. So what the inverse function theorem does in general is, if you're given the original function f, but you're unable to calculate what its inverse function is, you're still able to calculate the derivative of the inverse function given just the original function. You will see what I mean by this when we do the example question. But firstly, let's have a look at the alternative form. So the alternative form of the inverse function theorem states that for any value c, which is just some particular value of x, the derivative of f inverse at c is equal to 1 over f dash of the inverse value at c. Okay, so what this does is it simplifies the formula so that there's no more g. The reason why this makes it simpler for me is because I don't have to try to figure out which function is the original one, which one is the inverse one when they give you a question. All I now need to look at is the form of the thing or the expression in the question, does it match up to the left hand side or the right hand side? If it matches up to the left hand side, I know that the value inside the brackets is going to correspond to this c here. If it matches up to the right hand side, I know the thing in the bracket will match up to this f inverse c here. Okay, and this will make more sense when I do the example question. So the first example question we're going to do has a few parts to it. The inverse function theorem will kick in part D, and ABC is just going to basically set us up with the inverse function theorem. The first question says, okay, overall the question is, the function f has a domain that goes from 0 to 1 and is defined by e to the power of x plus ax, where a is a positive constant. Part A asks you to prove that 2 is in the range of f. So this will link back to what was taught in the previous section, which includes the intermediate value theorem. I'll quickly crop this question and put it onto OneNote so I can illustrate what I mean. Okay, so for part A, there's 3 conditions we need to meet. Okay, so the first condition is that the function has to be continuous, and then we also have to prove that the value 2 lies between the lower bound of f and the upper bound of f. Okay, so why is this important? If we have just any sort of function here, let's say the graph looks something like this. Okay, this function here is continuous, and if we have the point 2 here, where we have, let's say this point here is 1 and this point here is 3, for example, if this function is continuous and we want to prove that 2 lies within this domain from here to here, it would be good if we could prove that the lower bound here is a value less than 2 and the upper bound here is a value greater than 2, because then that means via the intermediate value theorem that 2 must lie within this portion here. Okay, so to do that, we first claim that fx is a continuous function, and that is true because it's simply an exponential plus a polynomial of degree 1. Okay, and then secondly, we have to prove that it has a lower bound that's smaller than 2 and an upper bound that's greater than 2. Okay, so if you look at the calculations here, when we plug in the lower bound of the domain, which is 0, into the function, we get 1, because we have e to the power of 0 plus a times 0. So that's just 1. Okay, and when we plug in the upper bound of the domain, which is 1, we get e to the power of 1 plus a times 1. So that's e plus a, which is what we have here. And given the fact that a is a positive constant, which is given in the question where a is a positive constant, we know that e plus a has to be greater than the value 2, because e plus a is going to be 2 point something plus a positive constant. Which then, if we go back to the graph we have here, we can erase this 3 and just make it e plus a. And then as you can clearly see, between this interval here from 0 to 1, 2 must lie within this interval, because the lower bound is smaller than 2, the upper bound is greater than 2, and it's also a continuous function. Okay, so that's part A done. Part B, prove that f has an inverse function. Now this goes back to the first theorem, which links the inverse function with one-to-oneness. Okay, so if we're able to prove that the function is one-to-one, then we will be able to prove that it has an inverse function. Okay, so one very common way to prove something is one-to-one is to check whether it's monotonic or not. Whether it's monotonically increasing or monotonically decreasing, that's okay. If we can prove either one, that's already enough for us to claim that the original function was one-to-one, and thus the inverse does exist. So to check whether the function is monotonic or not, we will look at its derivative. Okay, so in part B, as you can see here, when we take the derivative of fx, we get f dash x equals e to the power of x plus a, and that's just because when you derive exponential, we get it back, and when you derive ax, you get a back. Okay. Now, since a is positive and the exponential function is always non-negative, or like always greater than 0, we have that overall this f dash x is always going to be positive. Okay. Since f dash x is always going to be positive, we can claim that f is going to be monotonically increasing. So if the function is monotonically increasing, as similar to how we drew it here, it means that for every single y function, it has to correspond to exactly one x function. For every single y value, it corresponds to exactly one x value. Right? So every y value here will correspond to exactly one unique x value. That means that this function is 1-to-1. And since it's 1-to-1, it has the inverse function, which is demonstrated by this first theorem here. It's similar to how most of you would have learned in high school the horizontal line test. Yeah, it's a similar concept. Okay, that proves that f has inverse function. Now, before we move on to part C, I'll just briefly say that if you haven't noticed already, the reason why in part D we can use the inverse function theorem is because this function here, it's actually very difficult to find its inverse explicitly. In fact, you wouldn't be able to, because this exponential and a polynomial is two different types of functions. So if you try to swap the x and y's around, you can't get a explicit equation for the inverse function. Yeah, which is why the inverse function theorem is useful in part D. Okay. So firstly, to do part C, it says find the domain of f inverse, and from again the first theorem, when you take the inverse, the range and domain flips around. So when we want to find the domain of f inverse, we want to find the range of the original function f. Okay, if we can find the range of f, then that will be equivalent to the domain of its inverse. So how can we find the range of f? Well, most of this has already been proven to us in part A and B, because part of part B we proved that it was monotonically increasing, and in part A we also claimed that it was continuous, which means that the range of fx over this domain 0-1 must be exactly at its endpoints, here and here. Okay, the reason is because the entire function is always increasing and it's always continuous, so that must mean that the endpoints from 0-1 of this interval must also be where the smallest point of its function value is and the greatest point of where its function value is. Okay, so that means if we just look at what we did in part A, we had shown that f0 was 1 and f1 is e plus a. So this must be the range of the original function f over the interval 0-1. Yeah. So as it says here, as previously calculated in part A, we have these two values as the function value of 0 and the function value of 1. And so the range of f must be 1 to e plus a, and so equivalently, the domain of f inverse must also be 1 to e plus a. Because like I said, from the first theorem, it claims that the range and domain will flip around when you take its inverse. Okay, so that's part C. Now finally part D, which is the inverse function theorem. This is where the alternative form of the inverse function theorem comes into play. I will crop both of these side by side so it's easier to visualize what I'm talking about. Okay. So again, I will remind you guys that the function here is e to the power of x plus ax, but because in this question we're assuming a is 1, we can get e to the power of x just plus x. Okay. Now, they want us to find the derivative of f inverse of e plus 1. The reason why this form makes much more sense to me, at least, than this form is because I can directly see what the question has given me. Right? So the question has given me e plus 1 in the brackets here. So f inverse dash e plus 1. So I know directly that this e plus 1 correlates to this c here. Okay, which makes things a lot easier for me because I don't have to go around and figure out whether is this thing here correlating to this thing here or this thing here. Okay, in the other form of the inverse function theorem. So now that I know that c has equal to e plus 1, I now have to just calculate what the f inverse of c is, which is the same as saying the f inverse of e plus 1. this is the same as asking you, as asking yourself, what value of x do I have to plug in to fx to give myself e plus 1, right? Because f inverse is just, like I said, the domain and range flip. So when I'm doing f inverse of e plus 1, it's the same as asking me what x value do I have to plug into fx to obtain e plus 1. Now if you look at the form of fx, which is e to the power of x plus x, that answer is simply 1, right? Because when I plug in x equals 1, I will get e to the power of 1 plus 1, which is exactly e plus 1. Right? This way, I've already calculated what this f inverse of c has to be. This f inverse of c has to equal to exactly just 1. And now this makes everything so much easier, because all I need to do now is calculate what is 1 over f dash of 1. Okay, and that'll be my answer. Okay, so let's have a look at the calculations here. In part D, so we have already calculated that the inverse of c is going to be 1, and we also have that f dash x is e to the power of x plus 1. Recall that a is now 1, so there's no longer e to the power of x plus ax, it's simply e to the power of x plus x. And so when we differentiate this, we get e to the power of x plus 1. Okay, and so when we plug everything into the formula, we get 1 over f dash of 1. So when we plug in x equals 1, we will simply get 1 over e plus 1. And that's our answer using the inverse function theorem. Okay, yeah, so that's why, so it's up to you, but I personally prefer this form because it directly tells me that the thing they give me in the question corresponds to the c. Okay, which then allows me to more easily calculate what this f inverse of c is. Okay, so that's the most popular type of question they'll probably ask you for inverse function theorem. The next section of inverse functions is going to be about trig. Okay, so this is a much smaller part, and would also be a part that you would have most likely done in high school as well. But we'll go through just 2 examples just to revise how to do these sort of inverse trig function questions. Okay, so there isn't much definitions or theorem here. It's just calculating these 2 values. Okay, so in part A, again, I'll crop out the 2 questions first. In part A, the way I like to do this is to firstly calculate what this thing on the inside is equal to. After I calculate that, then I go over and think about the sine inverse. Right? So I think about what values does sine inverse accept. Okay. Now, what do I mean by accept? I'll quickly explain what that means again. So, if we look at the graph of sine, for example, it is going to be like this. The values that sine inverse will accept would basically be where can I create cut off the original function such that it passes the horizontal line test, right? So from here, the peak here is pi and 2. And this peak here, or this lower peak here is negative pi and 2, right? And so I then know that sine inverse will accept values between negative pi and 2 and pi and 2, right? Because the domain of the sine function the domain of the sine function that we're using here is from negative pi and 2 to pi and 2. And so again, since the domain and range flips, we now have that the range of sine inverse will be equal to negative pi and 2 to pi and 2. Okay. So with that in mind, after we calculate what this value is, we can then just try to get a value that is equal, like that will make sense with this value here, but between the range negative pi and 2 to pi and 2. Okay. So cos 3 pi and 4, what is that first? That is the same as saying cos of 135 degrees, which is basically cos 45 degrees in the second quadrant. That would be negative cos 45, which will be negative 1 on root 2. Okay. Now we're looking at what is the value of sine inverse of negative 1 on root 2. Okay. So usually there would be 2 answers to this, because if you think about it, there's 2 quadrants in which sine can produce you a negative value, right? But then if we go and consider the actual values that sine inverse can spit out, it has to be between negative pi and 2 and pi and 2, which means only the first quadrant and the fourth quadrant, correct? So what quadrant will give you a negative sign value? That has to be the fourth quadrant, right? So the fourth quadrant for the sign will give you will give you negative values because of the ASTC. So ASTC, right? And so the value that we should actually have would be negative pi and 2. Negative pi and 4. That should be our answer, because negative pi and 4 lies between negative pi and 2 and pi and 2, and we also know that sine of negative pi and 4 gives you negative 1 and root 2. Yeah. So basically, the way I like to do questions like part A is to firstly calculate this thing on the inside, and then think about what values does sine inverse accept, and then work backwards to figure out, okay, within these quadrants, what value, what value of, or like what angle will spit back out this value here. Okay. Good. Okay. Now in part B, this is kind of like the opposite of what's in part A, right? So part A had the inverse and then the normal trig function. This has the normal trig function and then the inverse. Okay. The way I like to do these is to draw a graph. Okay. So if I have a look at this question here, cos inverse of 3 on 5. Okay. So cos, remember, is adjacent over hypotenuse. So that would mean that you have 3 on here, and the hypotenuse here is 5. Oops. Okay. And this angle here would have to be your cos inverse of 3 on 5, right? Because you have adjacent over hypotenuse here. Okay. And just by Pythagoras, this vertical component must be 4. Okay. And then now if we calculate what is sine of this angle here, well, sine is simply just opposite over hypotenuse, so it simply just be 4 on 5. Okay, so it's just sine of cos inverse of 3 on 5 will just be equal to 4 on 5. Okay. So for part B, I like to just draw out the triangle on the xy plane, and then it's very easy to observe what the answer would be. If they decided to do something a bit different, so rather than it just being in the first quadrant, which is quite nice, if they gave you if they gave you this, for example, instead, say cos inverse of negative 3 on 5, you would just draw it in the second quadrant. So you would just draw it here instead, because we have a negative 3. Okay, and the hypotenuse is always positive, so that's still going to be 5. And this angle here will now be your cos inverse negative 3 on 5, right? And again, this vertical component is still 4, right? And so we have sine of cos inverse negative 3 on 5 is also 4 on 5. Right, which makes sense, because sine should be positive in both the first quadrant and the second quadrant. Okay, yeah. So just depending on what they give you here, draw the triangle in the corresponding quadrant. Yeah. So if everything is positive, just do it in the first quadrant. If one of them is negative, think about which quadrant is cos or whatever angle here is, like what quadrant are they negative in. Okay, and then draw the corresponding triangle, and then calculate the corresponding trig identity. Okay, that is basically it for inverse functions. So there's mainly 2 types of questions. One that concerns inverse function theorem, and the other one that they might ask you about trig. Okay, the next topic is curve sketching. Again, curve sketching has 2 main things. One is going to be just drawing a graph with weird asymptotes, and the other one would be using polar coordinates. Okay. So firstly, I'll go through the oblique asymptote ones. So it says, suppose that a and b are real numbers and that a is non-zero. We say that a straight line given by the equation y equals ax plus b is an oblique asymptote for a function f if, and this statement is basically saying, if the difference between the original function and the straight line approaches 0. So it's similar to just a definition of an asymptote, right? So if the actual function approaches a straight line, then it's an asymptote, right? The only difference here now compared to the usual asymptotes you would have seen is that they don't have to be just vertical or just horizontal. Okay. So let's have a question here. The question says, sketch 3x squared minus 4 over x plus 2. Okay. So you would still go through this similar, like a similar process as any other curve sketching question. So you want to find the intersections, any possible asymptotes, and then you can graph it. Sometimes, just a note here, some questions may also ask you to find the turning points or the inflection points, but in this case, it's not necessary. Okay, so the first step I would do is to find the x and y intercepts. Okay, so when x is 0, y is -2, and then y is 0, x is plus minus 2 and root 3. I'll quickly go through how we get those values. So just to recall, we have, that is our question. Let me move it first. Okay, and so if we just have y equals 3x squared minus 4 over x plus 2, when x is 0, there's a question here. From before, am I correct in saying that we were talking about sine inverse x as being the inverse function of sine as opposed to arc sine? We were talking about sine inverse as in arc sine and cos inverse as in arc cos. Does that answer your question? If they wanted to do 1 over sine, for example, they would probably have done that, rather than this. Yeah. So yeah, what Janila said there. Yeah. So the notation for 1 over would be this. Yeah. Okay. Let's move back to oblique asymptotes. Okay. So when x equals 0 here, we would have y equals 3/0 squared minus 4 over 0 plus 2. And so then we would have minus 4 and 2, which is equal to minus 2. Right, which is how we got when x equals 0, y equals minus 2. Yep. Okay. And then to find the x-intercepts, we would plug in when y equals 0, and then we solve for x. So when y equals 0, we would have 0 equals 3x squared minus 4 over x plus 2. If we just assume that x is not going to be -2, which is why we have an asymptote later, so if x is not equal to -2, then we have 3x squared minus 4 equals 0. And so then x squared equals 4 and 3. And so then x equals to plus minus 2 on root 3. And that's how we obtained our y and x intercepts. Okay. Now to find the asymptotes, the first one that we should observe is the vertical one, which is just simply when the denominator equals to 0. Yeah, which we have already shown here. So when x equals -2, the bottom will become 0, which then will make the value go to infinity, which then will become an asymptote. So when x equals -2, we have a vertical asymptote. Okay. In part 3, we're finding the oblique asymptote. So unlike the usual questions, there's no horizontal asymptote here, but instead there's one that is oblique. Right. The way that we can tell that there's no horizontal asymptote is because if we take the limit of x approaching infinity, this thing won't converge necessarily, right? So it won't converge to a nice constant. Okay. So to find the oblique asymptote, you can use long division or just use any other method to be able to separate out or factorize out the x plus 2 in the bottom. I personally here like to use manipulation, so I'll quickly explain what I did here, just to make sure it's not too confusing. So I knew that in the bottom I wanted to get out the x plus 2, right? I want to factorize the x plus 2. So I purposely added on a 6x here, such that when I factorize out 3x, I'll be left with x plus 2. Alright? And then after that, I purposely minus out 6x because in the original numerator here, we did not have a plus 6x. So I had to compensate for having added a positive 6x there by subtracting 6x. And then again, I have to minus 12. The reason is because I want to force it such that when I factorize out minus 6 in this case, I get x plus 2. Right? And then again, I have to add on an extra constant because I need to compensate for this minus 4 here. Right? I only had a minus 4, but I'm minus 12 here. So I have to add 8 back to get back to minus 4. And then if we factorize the thing out, so we cancel these out, we're left with 3x minus 6 plus 8 over x plus 2. Okay, So you can get the same result by doing long division. I just prefer to do it by manipulation here. Okay. And then if we do this like the usual thing of how we find horizontal asymptotes, we want to take the limit as x approaches infinity. Okay. So the limit as x approaches infinity of 3x minus 6 plus 8 over x plus 2. Okay. So as x approaches infinity here, this term here will shoot off to become 0, right? Because it's going to be 8 divided by a very large value, which will basically leave us with the line 3x minus 6. Okay. So this tends towards 3x minus 6. Okay. Which means that this will be our oblique asymptote. Okay. So now we're basically ready to graph, right? We have both asymptotes and we have the intercepts, and the question then asks us to find any turning points or inflection points and so on. And so if we just graph this real quick, so in part 4 we're going to graph it. We'd have x-axis, y-axis, and the two, or like the intercepts was when x is 0, y is minus 2, so that may be here. Okay, when y is 0, x is plus minus 2 and root 3, and 2 and root 3 is approximately 1.15, so it'd be maybe around here. I'll just put it there, 2 and root 3, and minus 2 and root 3. Okay, and we also have a vertical asymptote at x equals minus 2. Yeah, so we would have a vertical asymptote around here. And we also have a oblique asymptote when it's y equals 3x minus 6, right? So y equals 3x minus 6 would have x-intercept of 2 and a y-intercept of minus 6. So this would be around 2 here, and minus 6 maybe here. Okay, so we have another asymptote here. Okay. Yep, so we have our two asymptotes. This is x equals minus 2, and this is this one here, y equals 3x minus 6. And so then if we just graph it, passing through the intercepts and making the lines tend towards asymptotes, we would have that on the right hand side, this branch here would be like this. Oops, shouldn't be curving like that. Yeah. Okay, so it's heading towards asymptote and it's passing through the two x-intercepts and that y-intercept. And then on the bottom here, there's a left branch, since it would be like hyperbolic, it will have this branch here. Okay, and that would be our graph of the function. Okay, does it make sense? Okay. All right. If you're worried that maybe perhaps the thing is here instead, that wouldn't make sense because as we have calculated the intercepts, there's no intercept here. Right? There's no intercept around here, so it can't be this branch here. Yeah, so it must be this bottom branch down here. Okay. All right. That should conclude the oblique asymptotes bit. Let's move on to having a look at polar coordinates instead. Okay. So polar coordinates is a different way to define, I guess, points on a plane. So it says let P be every point on a plane, and the pair of parameters r and theta will then define the distance that the point P is from the origin, and also the angle between the line OP, or the segment OP, and the positive horizontal axis. So if you visualize what this means, just means that on the xy plane again, let's say we just have a random circle here with radius of r. A point P, for example, let's say here, will have its radius, which is r, and an angle to the horizontal axis here, the x-axis, and that will be theta. Okay, so that's another way to define the point P, right? So instead of just having its x and y coordinates, we have it in terms of r and theta. Okay, where theta defines the angle and r defines the length. Okay, so the Cartesian coordinates for like the parametrization of the polar coordinates in terms of Cartesian coordinates is x equals r cos theta and y equals r sine theta. The way we get this is simply if we look at the horizontal and vertical components of this point. Right? For example, if we have if we draw the triangle down to here, this right angle triangle, this x component here would simply be r cos theta, right? Because it would be cos theta would be adjacent over hypotenuse, and so this bit is just r cos theta. And this y component bit here would just be r sine theta, because sine theta is opposite over hypotenuse, so we would have y equals r sine theta. Okay, so that's how we get the parametrization for the polar coordinates in terms of Cartesian. Right? So we get x equals r cos theta, and y equals r sine theta. Okay, this will be useful because most questions will ask you to convert polar coordinates into Cartesian coordinates before doing anything else. Okay, so an example we have here, we have that a curve is in r squared, and it's given by the polar coordinates r equals 6 sine theta, where theta ranges between 0 and pi and 2. Express the equation in terms of Cartesian coordinates and state the range of x and the range of y. Okay, so to do part A, we're going to make use of this parametrization we have here. Okay, so in part A, using the fact that x equals r cos theta and y equals r sine theta, we have that x will equal 6 sine theta cos theta. The reason is because r in this case was defined as 6 sine theta. Okay, so we have x equals 6 sine theta cos theta, and we will have y equals 6 sine squared theta. Right, so again, 6 sine theta times sine theta. Okay, and then we just do some algebra here. So if we take this first equation and just rearrange for sine theta, we will end up with sine theta equals x over 6 cos theta. We can then sub in this into our y, and we get y equals to 6x squared over 6 squared cos squared theta, right? Because sine squared theta here, so we have to square this term. So x squared over 6 squared cos squared, which then gives us x squared over 6, because 6 and 36 will cancel out, and we're left with 1 minus sine squared, right? So we're just using the trig identity here. And then furthermore, as y is 6 sine squared theta, we can then rearrange for sine squared, and we get y on 6, which we can then plug back into here. And we're going to end up with, after just rearranging everything, we're going to end up with x squared plus y squared minus 6y equals 0. And from here, you should be able to observe that this is in the form where if you complete the square, you end up with a circle, right? And so that's what we actually do. We're going to get x squared plus y squared minus 6y plus 9 on both sides will then give us x squared plus y minus 3 bracket squared equals 9. So this will give us the circle centered at 0, 3 with radius 3. Okay, yeah, so this whole thing is just, part A is mainly just all algebra, and then observing that the thing you end up with is in the form of a circle. Okay, yeah, so that should be pretty easy. And then part B, they then ask you to graph it. Okay, wait, my bad. In part A, they also ask you to state the range of x and y. We'll do that first. The thing here is, although it's a circle, it's not an entire circle. Okay, and we can see that by this condition here. They gave us that theta had to be between 0 and pi and 2. If you have a look at the polar coordinates again, that must mean that every point of this graph has to be in the first quadrant, because theta ranges from 0 to pi and 2 only here, right, in this first quadrant, right? So anything you draw, or anything or like any points you obtain, they must all lie within the first quadrant. Okay, so again, if we look at our actual circle here, we have this, right? And so if we quickly just sketch this out, we will have centered at 0, 3 with radius 3. So it looks something like this usually, right? It would usually be a circle that has a radius of 3 and centered at 0, 3. However, since theta only ranges between 0 and pi and 2, we will only accept the first quadrant section of this graph. We will only accept here to here, right? And we will get rid of this section, right? Because this section would then go all the way to pi, right? So theta would range all the way to pi if we went to here. Okay. So then this will help us answer part B, and it will also help us answer part A, because then when we are asked for the range of x and y, we can observe that x only goes from 0 to 3. And y will go from 0 to 6. Yeah, does that make sense? So although we have a circle, we only have half of the circle because our theta had to range between 0 and pi and 2, which means it only lies within the first quadrant. Okay? And so this will answer both part A and B for us. Yeah. So part A, since theta is in this range, we only have the first quadrant section of the graph, and so x goes between 0 and 3, and y goes between 0 and 6. Okay? And then we graphed half the circle here. Okay. Okay, good. That basically concludes it for curve sketching. Right, so curve sketching was mainly graphing functions with weird asymptotes and also graphing polar coordinates. Okay. The next section we have is integration, which is one of the bigger topics in these 5 sections. There's a few theorems in integration and also a few techniques you need to know. I'll go through the first 2 theorems, which is the first fundamental theorem of calculus and the second fundamental theorem of calculus. The first one claims that if f is continuous and is defined on the closed interval a to b, then the capital F function takes the domain from a to b to the real values. Okay, and essentially f you can think of as being defined as the integral of the lowercase f. Okay, so f, like capital F here, is the integral from a to x, right, where a is the lower bound of this interval, to whatever value of x, of the lowercase fx dx. Okay, which is equivalent to saying that which is equivalent of saying that f dash x, the capital F here, is simply equal to the original function fx. Yeah. So like I said, you can think of it as simply as the capital F is the integral of fx, and so when you differentiate capital F, you simply get the original fx back. Okay, that's essentially what the first fundamental theorem of calculus is. The second fundamental theorem of calculus is one that is more widely used in questions, which is saying that when you take the integral of something, you just end up with capital F when you plug in its boundary points, right? So if you integrate lowercase f from a to b, it will simply be this capital F function that we defined in the previous theorem, which is the antiderivative of lowercase f, where you plug in the upper bound b minus when you plug in the lower bound a. Okay, yeah. So that's the 2 fundamental theorems of calculus that we're going to use for the next question. Okay. So in question 1, the first example we're going to do for integration, we have find this thing here. Right. So this looks really complicated at the moment. It has a derivative. It also has integrals, where its boundaries are also non-constants, right? They're x squared and x cubed. Okay. So the first step to do this is to use the first fundamental theorem of calculus and to define this thing inside the integral here, cos 1 on t, as the capital or as a derivative of the capital F. Okay. So let's first define the antiderivative of cos 1 on t as capital Ft, such that when you differentiate capital F of t, you get cos of 1 on t, which is what this first theorem says, right? This will be useful because then we can apply the second fundamental theorem of calculus, which required the capital F to be defined, right? So we have that the integral of cos 1 on t from x squared to x cubed will be equal to capital F of the upper bound x cubed minus capital F of the lower bound x squared. Yeah, which is just the second fundamental theorem of calculus here. All right. And so then, now that we have simplified this integral here, we simply have to take the derivative of this thing. Okay. This is where you have to be careful and use chain rule, right? So when you're differentiating each of these terms, you have to notice that the input you put here is x cubed and x squared respectively, which means when you differentiate in terms of x, you also have to differentiate the inner function, which is x cubed, and the inner function, which is x squared. Okay, so when we differentiate that, we get 3x squared f dash x cubed minus 2x f dash x squared, which is simply the derivative of 3x squared times f dash minus the derivative of 2x the derivative of x squared times f dash. Okay. If you're a bit confused as to how we get this here, I'll quickly write out the chain rule for this, because chain rule doesn't usually look like this. But if you have the derivative of f of x cubed, for example, dx, using chain rule, we can rewrite it like this. Times d of x cubed dx, which then gives you f dash x cubed times 3x squared, right? Which is why we get this term out here. And similarly for this term here. Okay, just in case you guys were confused about how to do chain rule when there's just a random function here that is not explicitly defined. Okay, all right. Now, okay, so now we go back to the definition of capital F that we did in the first part here. We define f dash t, capital F, as cos 1 on t, and so then we can just plug in this t equals x cubed and t equals x squared into this expression here. And so we ultimately have that the derivative of this integral is equal to 3x squared times cos of 1 on x cubed minus 2x times cos of 1 on x squared, where we simply just plugged in x cubed for t here, and we plugged in x squared for t here. Okay, does this make sense? Yeah. So we used both fundamental theorems of calculus to do this question here. Okay. The next part of integration is mainly integration techniques, right? There's integration by substitution, by parts, and so on. But the main one that you guys may not be too comfortable with is by parts. Okay. So by parts, the formula here is the integral of u times v dash is equal to uv minus the integral of v times u dash. Okay. So to do this, I usually like to set it up by finding out what all the u's, the v's, the u dash, and v dashes are. Okay. It will make more sense in the working out that I show you for this question here. So it says evaluate e to the power of x sine x dx. Okay. So the first thing we're going to do is define this integral as the capital letter I. Okay. Not all integration questions will require this, but for this particular question, this is useful because in the end, we will end up with another I term on the right hand side, which we can then rearrange to solve for I, right? But that's only because this question is designed the way it was, right? So sometimes the questions don't require you to define it as I, because doing integration by parts one time will be enough already. Okay, so to prepare for the first integration by parts, we have to pick out what we choose as u and what we choose as v dash. Usually the convention is to choose v dash first by choosing the easier thing to integrate, right? Because the v dash, to convert back to v, you have to integrate whatever you chose as v dash, right? So it's going to be more annoying if you chose something that's difficult to integrate, right? So in this case, I chose e to the power of x as my v dash because integrating e to the power of x will simply give me e to the power of x back. Okay? So I chose u as sine x and v dash as e to the power of x. When I differentiate u, I get cos x. When I integrate v dash, I get e to the power of x back. I then plug everything into the formula, which says that it's equal to u times v. So u times v, e to the power of x sine x, minus the integral of v times u dash. So e to the power of x times cos x. Okay. Now, as you can see, we're not quite done yet because this integral here is not that much better than the original integral we started with, right? Because this was e to the power of x sine x, this is e to the power of x cos x. We still don't have an explicit way of solving this integral. Okay, but what you should notice is that every time I apply integration by parts, this sine and this cos keeps alternating, right? It alternates between sine and cos, which means if I integrate by parts again, I should end up with e to the power of x sine x again somewhere, right? Which is simply my I. That's why I defined it as I initially, because then I can rearrange everything in the end. Okay. So if we apply integration by parts again, we then have to prepare. We then have to prepare for integration by parts again. So I will choose v dash to be e to the power of x because that's easier to integrate, and choose my u as cos x. If my u is cos x, then my u dash is minus sine x. If my v dash is e to the power of x, then my v is e to the power of x. And then I again use the formula. So I would have e to the power of x cos x, which is u times v, and I'll have minus integral of v dash, of v times u dash, which would be e to the power of x minus sine x, and dx, right? And so as you can see, this term here is actually just the same as my I, right? E to the power of x sine x, right? Which is why it will allow me to rearrange everything and get the answer in the end. So as I is simply the integral of e to the power of x sine x, I will rewrite this line here as I equals e to the power of x sine x minus e to the power of x cos x plus I. I then expand out the negative and move my I over to get 2I equals to e to the power of x in bracket sine x minus cos x. I then divide the 2 over, and don't forget to add c in the end, because in this case we were dealing with a indefinite integral, right? Which means we need to add the constant c. And that's how you would apply integration by parts to this question in particular. So again, as a remark, not all questions will require you to do parts twice, and also not all questions will require you to first define the function as I, okay, or the integral as I, okay. Yep. All right. Okay. The final part of integration that I'll go through is the comparisons, like the comparison test to check whether a integral converges or diverges. Okay. So this is to do with improper integrals. So the boundaries are not necessarily just a nice constant, right? It will go from something to infinity. Okay. So the comparison test is kind of similar to the stuff you've done in limits, potentially, about like the pinching theorem and so on. So it says that if we have two integrable functions, f and g, and gx is greater than fx, we then have that the improper integral of gx, if that converges, then the improper integral of fx must also converge. And this just intuitively makes sense, because gx is greater than fx, right? So if gx converges, then of course the thing that's smaller than gx must also converge. Okay. And similarly in part I, we use a similar argument. We say that if the improper integral of fx diverges, then the improper integral of gx must also diverge. And that again makes sense, because since gx is greater than fx, if fx already diverges, then the thing greater than fx must also diverge. Okay. So we're going to use this test to do question 3. Okay. Determine with reasons why the improper integral k converges or diverges. Okay. So usually to do the comparison test, we have to find an appropriate f or g depending on whether you want to prove whether it converges or diverges. In this case, we want to prove that this converges. Okay. So we want to be able to find a appropriate g to make this make sense. Okay. So we have that the function, so the thing inside the integral here, is 1 on e to the power of 2x plus cos squared x. So 1 over e to the power of 2x plus cos squared x here. And we have to find an appropriate gx. Okay. Cos x usually lies between -1 and 1, and so cos squared x usually lies between 0 and 1. Right? And so that means 1 over e to the power of 2x should be greater or equal to 1 over e to the power of 2x plus cos squared x. Yeah, simply because cos squared x is between 0 and 1, so this fraction must be smaller. Okay. And so it would be appropriate to choose g as 1 over e to the power of 2x. Okay. We can then use the p-convergence test on the improper integral g to check whether it converges. Right. So the p-convergence test is another test that is much simpler, and you guys should already know, whether it's from limits work or from earlier sections of integration. But basically, what it's saying is 1 on x does not converge, but then if you have 1 on x, the power of 1 point, even like 0.0000001, this will always converge, right? So as long as we have this p-value here is strictly greater than 1, no matter how much bigger than 1, then that will always converge, right? And so if we look at our g here, we have 1 over e to the power of 2x. And clearly e to the power of 2x is going to grow much faster than just x for values of x greater than 1, right? Which means we can apply the p-convergence test to say that the improper integral of gx will indeed converge, right? So yeah, so like I said before, e to the power of 2x is clearly bigger than x to the power of 1 for any value of x greater than 1. And so this will indeed converge. And the reason why we only care about x greater than 1 is because this integral can be rewritten as this anyways. So if we written as this. So and this is fixed, right? It goes from 0 to 1. So this will obviously be okay. And if we prove that this converges, then this entire thing will converge in the end. Okay. And so now that we've proven gx does indeed converge, we can then use the comparison test to say that, well, since g is bigger than f, and since the improper integral of g converges, then of course the improper integral of f must also converge. Okay. So that's how you would use the comparison test, for example. If you wanted to prove that it diverges, you do vice versa. So you would try to find an appropriate f that is smaller than g, and show that this f does indeed diverge, and if f diverges, then the function you have to begin with also diverges. Okay? That's it for integration. So there's the three main sections. So the first section was the fundamental theorems. The second section was just integration using various techniques. In this case, I went through by parts. And then finally, we had checking whether improper integrals converges or diverges. Okay. Now the last few sections are quite short, right? So the last few sections, logs and exponentials, you guys should all be kind of familiar with from high school already. So I'll just go straight into a question. And finally, for hyperbolic functions, it's a new topic, but all the questions always boil back down to the definition. So I'll quickly go through that in the end as well. But let's have a look at one of the questions from log and exponentials. Okay. It says, use log differentiation to calculate dy on dx when the value is y equals sine x to the power of x. Okay, so in this case we're going to be applying log rules and also log differentiation, right? So by logging both sides, we'll end up with ln y equals to x ln sine x, right? So by log rules, I can bring this x down to the front as a coefficient. Okay, then by implicit differentiation, we get that the left-hand side becomes 1 on y, dy on dx. The reason why we get an extra dy on dx term here is because y is inherently a function of x, right? And so when we differentiate this, we have to apply chain rule. We need to differentiate like ln y normally, so just 1 on y, but then we must also times it by the dy on dx term because y is a function of x. Okay, and on the right-hand side, we just use product rule, right? So we have ln sine x times the derivative of x plus x times the derivative of ln sine x. And again, for ln sine x here, we have to apply chain rules, right? So the inside function becomes cos x, the outside function becomes 1 on sine x. So we get cos x and sine x in the end. Okay? And so in the end, when we cross times this 1 on y over, we get dy on dx equals to y times ln sine x plus y times x cot x, because cos on sine is cot x. Okay? And since y is sine x to the power of x, we can plug that back into y. Then we simply get dy and dx equals to the y term, which is sine x to the power of x, factorized out, and in the brackets, ln sine x plus x cot x. Okay. Yep. So for log and exponentials, like I said, most of the questions will be stuff that you have already covered back in high school. So most of them are just log differentiation, maybe some log and exponentials graphing, and using like log rules. Okay. All right. Now the final section of MATH1131 and 1141 is hyperbolic functions. So this is something that will be new to most of you, and there's two main definitions they provide you with. One is cos x and one is sin x. This is say tan x and all the other ones, but all the other ones can easily be defined if you know what cos x and sin x is, right? So let's get through the first definition. The hyperbolic cosine function is defined by the formula cos x equals to half times e to the power of x plus e to the power of negative x. Okay, and hyperbolic sine is defined as half times e to the power of x minus e to the power of negative x. Okay, so as you can see, as long as you memorize one of them, the other one should be pretty easy. Just change the sign to the opposite. Okay. Now, if you're wondering, for example, what the hyperbolic tan is, for example, well, the normal trig rules still kind of apply to some degree. So tan would still be kind of like sine over cos, right? But of course, this time it's sine over cos, which is going to give you half e to the power of x minus e to the power of negative x over half e to the power of x plus e to the power of negative x. The halves cancel, and so you're just left with this. Oops. Okay. Yeah. So it's similar to just tan equals sine over cos, but this time we're doing it with hyperbolics. Okay. Okay. Now, if we move on to the first, the question that we have, most questions will be similar to this, right? They will usually always ask you to go back to the definition to prove something, or they may ask you to prove something maybe using the derivatives of hyperbolic functions. But even then, that still goes back to the definition, right? I'll go through this example first, and I'll briefly touch on the differentiation of cosh and sine, and then that we probably end it there. But firstly, in question 1 here, give the definition of cosh, that's just up here, right? Cosh equals 1 on 2 e to the power of x plus e to the power of negative x. And it says in part B, use the definition to prove that 4 cosh cubed x equals to cosh 3x plus 3 cosh x, right? So, by the definition of cosh x, we would have that 4 cosh cubed x is equal to 4 times, in brackets, half e to the power of x plus e to the power of negative x, all cubed. Okay? And then if we cube this thing, this half becomes 1 on 8. And then by Pascal's, we will get this thing for e to the power of x plus e to the power of negative x cubed. If you're confused as to how I got this line, I will quickly show. So if we have e to the power of x plus e to the power of negative x cubed, if we do Pascal's, which is going to give you this, we'll then have e to the power of 3x plus 3 times e to the power of 2x times e to the power of minus x plus 3 e to the power of x times e to the power of minus 2x plus e to the power of minus 3x. And then if we simplify this thing, this would become e to the power of x. If we simplify this thing, this would become e to the power of minus x. And so we end up with this line in here. Okay? And now if we keep going, this 4 and 1 on 8 can be simplified to become a half. And if you notice, within this bracket here, we already kind of have the core of what's on the right hand side, right? The right hand side said cosh 3x plus 3 cosh x. Cosh 3x would simply be when you replace the x of 3x, so e to the power of 3x plus e to the power of minus 3x on 2, right? And so if you notice what's inside these brackets here, we have the e to the power of 3x, and we also have that e to the power of negative 3x already. And so we're going to purposely group that together, okay? And similarly, we also want 3 cosh x, and as you can see, that's also already here for us. That's 3 to the power of, that's 3 times e to the power of x plus 3 times e to the power of negative x. And so if we purposely group that together, we'll get 3 outside of brackets e to the power of x plus e to the power of minus x, right? We then times this half into the square brackets, and we get half times e to the power of 3x plus e to the power of minus 3x plus 3 times half times e to the power of x plus e to the power of minus x. We then have, by definition, cosh 3x and 3 cosh x. And so we have finally proven that left hand side equals the right hand side. Okay? And we have proven this identity here. Alright? So as you can see, for this proof, we simply went back to the definition of what cosh was, and everything just makes sense in the end. Okay. Now, like I said, I'll briefly touch on the differentiation of cosh and sine. Right. So, for example, if you're asked to find out what sine dash x is, we'll simply go back to the definition of what sine is. Right. So sine was this: e to the power of x minus e to the power of minus x on 2. Right. So when we differentiate this, it's very easy, right? Because when you differentiate e to the power of x, you get the same thing back. So when you differentiate this, you simply end up with e to the power of x minus e to the power of negative x on 2, which is e to the power of x plus e to the power of minus x on 2, which is cos x, right? And similarly, if you do cos of dash x, you remember that the definition of cos x is e to the power of x plus e to the power of minus x on 2, and so the derivative of cos x will simply be e to the power of x minus e to the power of minus x over 2, which is, yeah. So even if they ask you to do anything with differentiation, you can always just go back to the definition of what sine and cos is, and everything will just make sense, right? So that's mainly it for hyperbolic functions, right? Just remember to always go back to definitions, and everything should work out in the end. Okay, that should conclude it for the entirety of the Math1131 and Math1141 course. Are there any other questions left? No? Okay, if everyone's good with that, then that should conclude today's session. I hope you all learned something from this session, and good luck for your exams. Okay? I will leave the stream on for like 5 more minutes in case anyone has any questions, and then after that I will just close it. Yeah, so you may all feel free to leave the session now. The session, well, we did just end just then. Was it pausing the entire time? Did anyone else have the same problem as Calvin? Graph drawing. Okay, which question did you need help with for graph drawing? Yep, all good. Did you need help with the polar coordinates or the asymptotes one? Right, okay, well, sorry everyone for the pausing, but yep. The latter, so the polar coordinates one? Oblique stuff, okay. Yep, so it's not that much different to the usual graphing. The only difference is instead of having horizontal asymptotes, you might end up with an asymptote that is not horizontal, right? So it might be slanted, okay? And the main thing is, okay, so everything else is the same as the usual graphing, right? When you find the intersections and when you look for when the denominator is equal to 0. The main difference is part 3 here, when you have to find out what the oblique asymptote is, right? So to find the oblique asymptote, your aim is to try factorize out the bottom. If you can factorize out the bottom, then you should be left with some like y equals mx plus b function plus something that's over the denominator, right? And then as you take the limit of x approaching infinity, you would then get that this term here approaches 0, right? In terms of how you can factorize out the bottom, you can do what you can try to do what I did here, where I use manipulation, but you can also just use long division or use inspection or any other method you prefer, right? But the key idea is to use any method you want to factorize out the bottom, so that you're left with a function in terms of y equals mx plus b, and this value here. Yeah. So it might not look exactly like this, right? The general form would be something like this, like mx plus b plus some constant over some function of x, such that when x goes towards infinity, this thing goes towards 0. How we got to step 3 in the first place? So step 3 didn't depend on step 1 and 2. It was simply a brand new step where we tried to factorize out the denominator to find the oblique asymptote. So step 3 is independent of part 1 and 2. In fact, every step should be independent of each other except for step 4. So step 1 is just finding the intersections by itself. Step 2 is just finding the vertical asymptote by itself, and step 3 was finding the oblique asymptote by itself. Or did you mean, how did I get to this expression here? It's not a completely different question. It's still the same question, but it's just a different step. So it doesn't have anything to do with part 1 or 2. If you're just given a... okay, how do we get to that equation? Right. So to do this, like I said, you can just use long division, but I used manipulation here where I purposely added these terms here so that I can factorize out x plus 2 in the end, right? Because as you can see, there's actually no difference between this here and this here. I plus 6 minus 6, that's just 0, and I minus 12 plus 8, that's just 4. But I just purposely added and minus terms so that I could factorize out x plus 2 in the end. But like I said, you can use long division instead if you want. Does that answer your question? Is it all good now? Yeah. Yeah, because then when you take the limits of x approaching infinity, the thing that's above x will just approach 0. So then you have an actual line that your asymptote, for your asymptote. Yep, so you just purposely want to use division so you end up with a term like this and another value here that will become your asymptote. So 8 on x plus 2 doesn't necessarily exactly go to 0, but it's just that it gets very, very small to the point where it's insignificant in comparison to 3x minus 6. Right. Yeah, I would say just maybe go through some other past papers that has an example like this, or play around Desmos. And you'll realize that the asymptote is always going to be this line here when you can get it into this form, right? As long as you can get it into this form, this term will always become insignificant in comparison to this other term out here. So when x gets really big, this term will dominate, and so it will become your asymptote. Yep. Did you have any other questions, or was that it? Okay, so for polar coordinates, okay, so the main thing for polar coordinates is you have to firstly just convert it into Cartesian. So you have that the r value here equals to 6 sine theta, and if you go back to this definition here, we have that the x coordinate equals to r cos theta, and the y coordinate equals to r sine theta, right? So when you go into figuring out part A, which asks you to convert it into Cartesian coordinates, you just want to plug it into that formula. So you have x equals to 6 sine theta cos theta. That's the same as r cos theta, because r is 6 sine theta. And for y, you get 6 sine theta, because again, y is just r sine theta, right? And then this entire section here is just all algebra, right? So you take the two equations and you solve simultaneously until you finally end up with this thing here, which is x squared plus y squared minus 6y equals 0. And hopefully you can observe that this is in the form of a circle. And so when you complete the square, you end up with a circle with a particular center and a particular radius. Yeah, and you can graph that. But before you graph it, you have to take note of what condition they gave you for theta. Right? In this case, theta is said to be between 0 and pi 2, which means the graph only exists in the first quadrant, because in the first quadrant, only do you have the angle goes from 0 to pi and 2. If it goes in the second quadrant, that'll be to all the way to pi. Third quadrant, all the way to 3 pi and 2, and if it's the entire way around, it's all the way to 3 pi, right? So since theta can only exist from 0 to pi and 2, if we take a look at the graph I drew back here, actually I'll just draw it again more neatly. We have a circle with center 3 and radius 3, but then only the first quadrant section exists. So only this section exists. Does that make sense? So this section out here does not exist because my theta is between pi on 2 and 0. So the main thing of polar coordinates is to understand how to convert it to Cartesian coordinates and then graph it in terms of x and y. Right? And I guess the geometric interpretation of the polar coordinates is just if you have a point P on here, it's simply just from the center, what's the radius and what's this angle theta. Yep, just square root 9. So the radius here is 3. Yeah, the radius of the circle is 3. So it's just a circle centered at 0, 3 with radius 3. But then you only take the first quadrant section because your theta ranges between 0 and pi and 2. Alright, good. Okay, that's it. Then I'll probably end the stream now. Alright. Good luck with the exam.